Welcome everyone to our third Break the Ice Lunar Challenge webinar. This webinar is focused on lunar surface emulation. It's about a 60-minute webinar, and at the end we will go into some Q&A. I will pass it over to Kurt, who is our SME, who will be leading this webinar. Just as a friendly reminder, we will be doing questions. Please input those into the Q&A box. And we will be getting to those questions at the end of the webinar. And then I'll also take some time to go through some of the team registration process, which is an upcoming event next week. It's a big deadline, so everyone who is interested in participating in this challenge, it is crucial that you submit your team registration form by next week. So we'll be sharing more information and guidance on that throughout this week and next. But with that, I will go ahead and pass it over to Kurt.
Thanks, Ollie. Can you hear me okay?
Yes.
All right. Hey, everybody. I'm Kurt Lloyd. As Ollie said, I work for NASA at the Kennedy Space Center in Florida, and I'm part of this amazing NASA Centennial Challenges program team who are planning and organizing and executing NASA's Break the Ice Lunar Challenge. Now, if you took part in our previous webinar, webinar number 2, which happened about a month ago, you learned about the icy regolith simulation element of our challenge, and you learned about controlled low-strength materials. If you missed that webinar, you can find it on the challenge website under Resources and Media. Now, this webinar, webinar number 3, is going to focus on the transportation simulation element of this challenge, or emulating the lunar surface for your 15-day-long durability demonstration test. I'm going to turn my camera off so as to not waste bandwidth during my presentation. All right, hopefully my screen is still being shared. So here is what the official challenge rules say about the transportation simulation element of this challenge. The rules say that the goal is to further development of certain technologies that can both excavate and transport large quantities of icy lunar regolith, and technologies that can address these technology gaps below. Technology gaps being excavation of large quantities of material, delivery of large quantities of material, lightweight and energy efficient equipment, reliable and durable equipment, and equipment that operates well in the extreme lunar environmental conditions, including reduced gravity and complex terrain, including rocks, craters, slopes, and loose granular soil. Now, I've highlighted the transportation simulation element focused words from this section of the rules. Those words that focus on the transportation simulation part of this challenge are transport, deliver, lightweight, energy efficient, reliable, durable, and all the details of the complex terrain that the equipment needs to operate in. The rules also say that the transportation part of this challenge will be demonstrated by hauling the material over a surface that simulates certain physical characteristics of the expected lunar surface. And the rules say, immediately after that, the rules say, rather than prescribing a specific track size, track shape, track length, roughness, layout, slope, track surface makeup, particle shape, mineralogy, size distribution, and compaction, this challenge allows each team to create their own transportation demonstration area that's capable of demonstrating and testing their hardware continuously for 15 days. And so this challenge is allowing each team to decide for themselves what physical characteristics of the lunar surface that they want to simulate or that they want to emulate at their own test site during phase 2, level 2. But there's a slight catch. Teams have to explain and they have to justify those decisions. So these words are also in the rules. I just copied and pasted them right out of the rules. The rules say that teams must explain and justify the extent to which their transportation demonstration area simulates the physical and environmental details of the anticipated lunar surface. Later in the rules, when you get down to level 1 deliverables, there's a deliverable called Durability Demonstration Test Plan. And that deliverable must include plans and justification for emulating the physical and environmental details of the anticipated lunar surface. Later on, there's a level 2 deliverable, which most teams probably aren't focusing on yet. That deliverable is called your durability demonstration test report. That's your report of how your test went and all the details of the test. And when you turn in that deliverable, it must include any changes to the prior deliverable, that level 1 deliverable, the demonstration test plan. And so after phase 2, level 2 deliverables are submitted by teams, the challenge judging panel is going to score the fidelity. They're going to score the fidelity of each team's lunar simulation, and they're going to score that weighted at 15% of your total score. They're going to judge the extent to which your transportation demonstration area simulates the physical and environmental details of the anticipated lunar surface. Same words as we saw before. And that is going to be judged based on information and justification that teams provide in their durability demonstration test plan, which is the level 1 deliverable I just talked about, and the team's durability demonstration test report, which is the level 2 deliverable I just mentioned. And so I hope I'm kind of going over these rules again, but I hope they were fairly clear when you first read them. And if not, hopefully they're clear now. What the rules are saying is that each team can decide how much effort and how much resources they want to spend on this area of the challenge based on the fact that the outcome of that effort is worth 15% of their total score for level 2. So because of this, some teams may say, hey, it's only 15%, let's not sweat it too much. While other teams may say, hey, that's 15%, so we really need to nail that part. And both of these extremes are perfectly fine. It's completely up to each team to decide where they want to land on that spectrum. But obviously, not everyone is a lunar surface expert. I work for NASA in ISRU research and development, and I don't even claim to be an expert. But there's this amazing lunar reference, and pretty much everything humanity currently knows about the moon is captured in this wonderful technical document called the Lunar Source Book. It's a big document. It's nearly 800 pages, but it was written to provide a single, complete, annotated description of our present knowledge of the moon. It's highly technical, but it's actually intended for a wide range of readers, including scientists who are studying the moon and trying to understand its place in the solar system, and for designers who are planning missions to return to the moon. And I think that's technically all of us here in today's meeting, right? And the Lunar Source Book is also written for engineers and astronauts who may participate in the future exploration of the moon. The Lunar Source Book contains a lot of excruciating detail about every aspect of the moon that you can imagine. So I'm just going to go over the highlights that I think are most relevant to teams like you who are trying to simulate or emulate the lunar surface for a transportation rover. By the way, if you want to review the Lunar Source Book in more detail, you don't have to buy it. The Lunar Source Book is available in digital form for free on the internet. Just search for those keywords, Lunar Source Book, and it'll pop right up. Okay, here's the moon, as most of us know it. When we look at the moon from afar, as a whole, we can clearly see distinct regions. We can see highlands and we can see low plains. The highlands on the moon are areas of mountains and valleys. The highlands are the lighter colored regions of the moon. They're also called terra, which is Latin for earth or land. The lowlands are areas of flat plains on the moon. They're darker colored regions that were once believed by ancient astronomers to be filled with water. They named these regions mare, which is Latin for sea, S-E-A-C. We now know that they are actually huge solidified pools of ancient lava. So it turns out naming them seas weren't that far off. They're just not seas of water, they were seas of lava. The detailed low-level mineralogy of the moon isn't necessarily critical for simulating its mechanical properties. But just really quickly, the most abundant minerals found in rocks on the moon are silicate minerals like pyroxene, feldspar, and olivine. Now, these are not photos of very colorful moon rocks. These photos show these three minerals in crystalline form here on Earth. The moon's terrain has been controlled by high velocity impacts and also by volcanism. The low-lying mare basins are surrounded by high mountains that were formed during impact by small solar system bodies. Many of these same low-lying basins were smoothed when they became filled with basaltic lavas. Now, basalt is a word that you may not be familiar with, but it's a word that you will hear quite a lot in geologic circles, especially in lunar geologic circles. Basalt is basically a fine-grained rock that is formed from the rapid cooling of lava. It's rich in magnesium and iron. Basalt is very common in the solar system, and more than 90% of all volcanic rock on Earth is basalt. And the low-lying lunar mare basins are also mostly basalt. The lunar highlands, which you recall are the lighter colored areas of the moon, they do contain some basalt, but they are mostly made up of feldspar, which I mentioned a couple slides ago. That difference in mineralogy between these two lunar regions at least partially explains the darker color of the mare and the lighter color of the highlands. Now back to the moon's terrain. Deep channels on the moon cut the low-lying mare surfaces, and faults and wrinkle ridges buckle those same low-lying surfaces. Craters are also an obvious feature of the lunar terrain. Basically, the entirety of the moon's surface is cratered. Craters range from subdued, shallow depressions to sharp-rimmed features littered with large boulders. Another major feature of the lunar surface is regolith. Regolith is a blanket of unconsolidated, loose, heterogeneous, superficial deposits covering solid rock. Regolith includes dust, broken rocks, and other related materials. Regolith is present on Earth, and the Moon, and Mars, and some asteroids, and other terrestrial planets and moons. Sometimes the phrase lunar soil is substituted for lunar regolith. They're the same thing. Nearly the entire lunar surface is covered with loose regolith, except on some very steep-sided crater walls where there may be exposed bedrock. This blanket of fine powdered regolith is thanks to meteoroid impacts, which have broken up and pulverized lunar bedrock for ages and ages and ages. The blanket of regolith is generally agreed to be about 4 to 5 meters thick in the low-lying mare areas and about 10 to 15 meters thick in the older highland regions. Lunar regolith has grain size characteristics similar to pebble-bearing or cobble-bearing silty sands. Many of the regolith grains are sharp and glassy. Here's a detailed grain size chart for regolith samples that were returned to Earth from the lunar surface. Just ignore the JSC 1A line in this chart. That's one of NASA's official lunar simulants. I tried to find a chart without any lunar simulant in it, and I just couldn't find one. So according to this chart, it turns out that the average grain size of regolith samples that were returned from the lunar surface is between 45 and 100 micrometers or microns. I'm going to pause here for a moment to let that number sink in. 100 microns is 1/10 of 1 millimeter. So that's pretty small. Lunar regolith is similar to baking flour or talcum powder as far as particle size is concerned. Analogies have been made to fine-grained slag or terrestrial volcanic ash, or to a dry silt bed in the desert, which means that medium and coarse sands and gravels don't really do a terrific job of simulating lunar regolith particle sizes. And it turns out that the shapes of individual lunar soil particles are highly variable. They range from spherical to extremely angular. In general, the particles are somewhat elongated and are subangular to angular. Because of the elongation, the particles tend to pack together with a preferred orientation of the long axis. Due to the earlier mentioned baking flour sized particles, plus this elongated particle-shaped packing feature, lunar regolith generally tends to be extremely light and fluffy on the surface, while also being fairly hard-packed below the surface. The hard-packed material can become light and fluffy, though, when disturbed mechanically. The best current estimate for the average bulk density of the top 15 centimeters of lunar soil is 1.5 grams per cubic centimeter, and of the top 60 centimeters, it's 1.66 grams per cubic centimeter. The best current estimate for the average cohesion of the top 15 centimeters is 0.52 kilopascals, and of the top 60 centimeters is 1.6 kilopascals. The best current estimate for the average friction angle of the top 15 centimeters of lunar soil is 42 degrees and 49 degrees in the top 60 centimeters. The mechanical properties of lunar soil are remarkably similar to those of terrestrial granular soils of comparable gradation, even though the chemical composition of the two soil types is not the same. According to all the testing we've performed, the mechanical behavior of lunar soil appears to be dominated by the particle size, the distribution, the particle shape, and the packing characteristics. Now let's talk about dust. This is a photo of Apollo astronaut Gene Cernan after returning to the safety and comfort of the lunar module after a long workday on the surface of the moon. And it's pretty obvious that he's filthy with dust, and so are his clothes, and so is his spacesuit. Apollo astronaut Al Bean said the following about moon dust. He said that after lunar liftoff, a great quantity of dust floated free inside the cabin in zero gravity. He said that this floating dust made breathing without his helmet difficult. And he said that enough particles were present in the cabin atmosphere to affect their vision. He also said that the use of a whisk broom prior to returning to the lander would probably not be satisfactory in solving the dust problem, because he said the dust tends to rub deeper into the garment rather than brush off. So what the astronauts and what the NASA engineers found out during Apollo was that the regolith dust particles ended up being a real nuisance to their cloth suits and to the soft rubber seals in those suits, to the astronauts' skin, their lungs, their eyeballs, etc. Now let's talk a bit about some details from a few of the Apollo landing sites. These details are from their logs after they returned. First, the Apollo 11 landing site. The Apollo 11 landing site is located on the flat surface of a mare or sea, but it's actually kind of pretty far from smooth. It's actually covered with craters that range in diameter from just a foot or so to 20 meters across. Plus, there's an occasional very large crater in the area. For example, a fresh 180-meter diameter crater that's 30 meters deep is located just 400 meters east of the Apollo 11 landing site. This large fresh crater is surrounded by a 250-meter wide swath of ejected rocks that are as large as 5 meters across. These are really big rocks. And this is the rock field that Neil Armstrong had to avoid during his landing sequence. The Apollo 14 landing site is located on a highland formation which is an elongated ridge that's a few kilometers wide and a few meters to tens of meters high. Large craters with diameters of half a kilometer to a kilometer are much more abundant here than in the mare or sea regions. The smooth terrain of the site is more or less level over distances of several kilometers, but it is saturated with craters that are several tens of meters to hundreds of meters in diameter and meters to tens of meters deep. The walls of the older, larger craters have slopes of 10 to 15 degrees. Apollo 16 landed on a heavily cratered lunar highlands plain. Not too far away from the landing site are the Descartes Highlands, which includes a half a kilometer high mountain called Stone Mountain. The slopes of Stone Mountain are subtly terraced and they have a maximum angle of 18 degrees. Smoky Mountain, which is located just north of the landing site, has a plateau-like top, but it is steep-sided with slopes up to 40 degrees. Both the plains and the hilly terrain at this site are heavily cratered. Two of the largest and youngest craters on this site that were studied by the Apollo 16 astronauts are a half a kilometer and a full kilometer in diameter, and are 100 meters and 200 meters deep, respectively. Most crater walls at this site are not steeper than 40 to 45 degrees. The walls of these craters are covered with loose, thin regolith, boulders, and some outcrops. South Ray Crater, which is the freshest large crater in the area, has a high concentration of large blocks near the crater rim. The astronauts noted that it would have been impossible to drive to the rim of this crater because of these large blocks. Now we're going to talk a bit about trafficability. Trafficability, if you're not familiar with the word, is defined as the capacity of a soil to support a vehicle and to provide sufficient traction for movement. Based on experience of the Apollo and the Lunar missions, we know that almost any vehicle with round wheels will perform satisfactorily on the lunar surface, as long as the ground contact pressure is no greater than about 7 to 10 kilopascals. As a wheeled vehicle travels on a level lunar surface, the energy consumed in overcoming the combined effect of surface roughness and rolling resistance, or soil compaction, is roughly equivalent to the energy expended in continuously climbing a smooth, rigid 1.5 degree slope. For the Apollo lunar roving vehicle, which carried 2 astronauts, the combined surface roughness and rolling resistance accounted for only 15% of the total energy expended. The remainder of the energy was lost to mechanical linkages, to inertia, to instrumentation, and etc. The primary limitations on the trafficability of the lunar soil are speed and slope climbing. The normal cruise speed of the Apollo lunar roving vehicle was 6 or 7 kilometers per hour. This speed was constrained by the irregularity of the cratered surface, coupled with the low lunar gravity. But the speed of a future lunar vehicle could be increased by modifying its dynamic response. In other words, by using larger diameter wheels, or an increased wheelbase, or a greater mass, or a softer suspension system. Or we could always just build permanent hard roads on the moon. This video from Apollo 16 is pretty great if you haven't already seen it. It was a high-speed lunar driving test that was requested by the LRV, Lunar Rover Vehicle Design Team, back in Mission Control. They called it the Lunar Grand Prix. Astronaut John Young was driving, and astronaut Charlie Duke was filming using a 16mm handheld camera. This particular video is restored, upsampled, and stabilized. I mentioned that the normal cruise speed of the LRV was about 6 or 7 kilometers per hour, but John Young actually went about twice that speed during this particular test. And it's a good thing he was strapped in because it wasn't a smooth ride by any means. A couple things you'll notice in this video is the rooster tails of regolith that are lofted while driving. You can imagine what a mess that would be if those fenders weren't there to catch most of the flying regolith. When the rover comes back to the starting position for another loop and drives slowly past the camera here in just a few seconds, you might even notice regolith being picked up by the wheels and carried all the way up and around and then dropped in front of the wheels. This occurs even at slow speeds. You might be able to tell that the back end of the LRV breaks loose and spins around during tight turns. John Young said that the high-speed Grand Prix test was like driving a Jeep on ice. It was quite a ride, apparently. And we're going to watch him come back around again. Now, you can find this video on YouTube. Just search for Apollo Grand Prix, Lunar Grand Prix, Apollo 16 Grand Prix. Any of those keywords will bring it right up for you. And that was the end of the Grand Prix. This part of the video is not from the Lunar Grand Prix, but it's a pretty great first-person LRV view that I found while I was looking for the Grand Prix footage. So I thought I would include it because it's just fun to watch the LRV's perspective, the astronaut's perspective. Get a pretty good view of the terrain and the rocks and the hills in the distance and the slopes. Just really great footage. Now, speaking of slopes, let's talk about the terrain slopes. I'm going to focus on the slopes near the South Pole, partly because that's the area that this challenge operates in, and partly because I had trouble finding high-resolution slope maps for the equatorial regions. So this slope map is centered on the lunar South Pole, and it marks any slopes over 15 degrees in red, which is maybe a little bit unfair if your robot doesn't have any problems with slopes over 15 degrees. So here's a higher fidelity slope map of roughly that same area. You can see that the slopes going down the rim to the bottom of Shackleton Crater are actually 30 degrees, which is pretty steep for a lot of rovers. But if we zoom in to the Break the Ice Lunar Challenge mission area, which is detailed in the Phase 1 challenge rules, and is roughly located off the 9 o'clock position of the rim of Shackleton Crater. And it includes a landing spot and a permanently shadowed excavation spot. When we zoom in there, you can see that there are very few slopes in this area above 25 degrees, which would be yellow colored or red colored. But there is a good amount of purple between the landing spot and the excavation spot, which indicates 15 to 20 degree slopes between those two sites. However, if a mission planning team wanted to avoid these 15 to 20 degree slopes, they could probably find a roundabout meandering path that stays under 15 degree slopes. But Phase 2 of this challenge does not transport water from the excavation area all the way back 4 kilometers to the landing area. Phase 2 only transports excavated icy regolith about 500 meters away from the excavation area, just far enough to get it up and out of the permanently shadowed crater. And so it's up to each Phase 2 challenge team to decide what slopes that short 500-meter trek will include. Just don't forget to justify that decision in your deliverables, as I stated earlier. So that was a quick high-level summary of what we currently know about the moon's surface. Now let's talk a bit about what we don't know about the moon's surface. The Apollo missions all concentrated near the equatorial regions of the moon, give or take. And they also taught us little or nothing about the lunar polar regions. Obviously, a lot more uncrewed lunar landings have occurred than crewed ones. But most uncrewed landers have also focused their attention away from the lunar poles. Nearly all of our lunar polar data has come from orbiting spacecraft that have sensed the surface from far away. All except Alcross, which deliberately crashed into a crater near the lunar south pole to look for water. So our knowledge about the lunar polar regions is pretty limited right now. But there's even more that we don't know about the lunar surface. The lunar samples that were brought back by the Apollo missions were a huge benefit to science, obviously, but even those samples were limited. All of the Apollo missions combined returned a total of 382 kilograms of lunar samples. 70% of that weight was rocks, 5% was cores, and 25% of that weight was fines. And so we actually only have about 95 kilograms of lunar regolith here on Earth for studying. That's a little over 200 pounds, which isn't a whole lot of lunar regolith. Well, I suppose it's a lot if you only need an ounce or two for your test or for your experiment, but if you needed tens or hundreds of pounds, you're just out of luck. So based on what we know and what we don't know, how does NASA and associated aerospace companies test and certify moon rovers for lunar surface missions? Now, I want to be clear here. I am not showing you Break the Ice Lunar Challenge teams this particular information because I think that you teams should test your challenge prototype machines to the same level of rigor that NASA does for our flight rovers. Testing a NASA Centennial Challenge non-flight ground demonstration prototype to the same level and rigor as a lunar mission flight rover would obviously be overkill. So let's start with the Apollo program's Lunar Roving Vehicle, or LRV. At the time that the LRV was being developed, no actual mobility performance data existed relating to wheel-soil interaction involving extremely light wheel loads and fine-grained, granular, slightly cohesive soils. And so extensive wheel-soil interaction experimental studies were performed at 1G and at ambient atmosphere in various research facilities. These tests used single prototype scale wheels and also wheeled mobility test beds that interacted with various lunar soil simulants. Now, before the mechanical properties of the Apollo 11 soil was ever known, the LRV team simulated lunar soil using a uniform dune sand from the Arizona desert. They called this simulant Yuma sand. But they soon switched to a new simulant that consisted of a finely ground basalt that they got from Napa, California. And this finely ground basalt had a grain size distribution very similar to that of the Apollo 11 soil samples. This improved simulant was called LSS-WES mix. And you can see both the Yuma sand and the LSS-WES mix in the chart. You can see how much better the LSS mix matched the shape of the Apollo samples also. Now, in addition, wheel-soil interaction tests were performed also inside vacuum chambers while flying on board parabolic jet flights that simulated 1/6 gravity using the same ground basalt lunar simulant. And before the actual flight of a lunar rover vehicle, a qualification test unit was built to the same specifications as the flight unit. And that unit was subjected to testing conditions that were many times more severe than those expected on an actual mission. It was over-tested. Once these qualification tests were finished, given the stresses that it had been subjected to, the qualification unit could not safely be used in space. but it can be seen on display at the Smithsonian National Air and Space Museum in DC if you want to go check it out. Now, over the years, NASA has been working on and tweaking the wire mesh tires that were used by the Apollo program's LRB. And fairly recently, NASA's come up with a new, tougher version, which uses shape memory alloys that can be used on very heavy rovers. This new tire can take a real beating, and it just springs back to its original shape with little or no deformation. This video shows a prototype taking a real beating without any ill effects. This particular test was performed at JPL in California, but NASA has several different facilities that focus on different aspects of mobility testing. This circular carousel JPL facility that's shown here is focused on sharp rocks and long duration lifetime testing. And NASA's Glenn Research Center in Cleveland, Ohio, has what they call their SLOPE Lab, which stands for Simulated Lunar Operations Lab. They have several large soil bins. They have a wheel dynamometer for measuring dynamic net tractions and sinkage and slip curves. And they also have a large adjustable tilt bed for testing rovers on sloped, loose, granular soil, which you can see in the background of this photo. And also NASA's Kennedy Space Center in Florida has what they call their SwampWorks facility, which is surprisingly not an acronym, but it's just a really cool name, SwampWorks. SwampWorks has a 25-foot by 25-foot enclosed bin filled nearly 4 feet deep with crushed basaltic rock. And that bin can be used for mobility testing, for excavation testing, for dusty soil testing, etc. Inside the bin, SwampWorks has a high-resolution 2-axis computer-controlled positioning system that can be used for precision excavation implement testing or for gravity offloading. So let's get back to testing and certifying actual NASA moon rovers for actual lunar surface missions. You may have heard of NASA's new VIPER moon rover. VIPER stands for Volatiles Investigating Polar Exploration Rover. It's basically a mobile coring drill with a mass spectrometer on board that can look for water in 1 meter deep core samples. VIPER has been tested quite a bit at NASA Glenn's SLOPE Lab throughout its development, starting with simple single-wheel dynamometer testing in simulated lunar soil and rocks, and then graduating to complete mobility subsystem testing in loose granular soil and rocks, and on slopes too. This video is pretty great. It shows a VIPER prototype being put through the ringer in the SLOPE Lab. You can see the technicians creating the craters and rocks. Downhill is obviously a piece of cake. Uphill is a bit harder. You can definitely notice some slip happening there. But that's well within its design range, its operational range, I'm sure. And rocks of a certain height obviously are not a problem. Now here's where the testing gets a little bit extreme though. This particular simulant that they're using is very light and fluffy, and it acts a little bit like quicksand. It really can bog down the rover. But VIPER has a few extreme mobility tricks up its sleeve and is able to get out of this super soft soil. VIPER can swim, it can inchworm, and it can crab. So all pretty cool maneuvers. Now, I am not suggesting that teams go to these extremes. These are just real-life examples of the rigor that NASA uses in order to lower the risk of real lunar missions. Obviously, VIPER is becoming a very costly robot the more capabilities that get added to it. But it's going to do some amazing science, so we really need to lower the risk as much as we can, and we think it's worth the money. And so in conclusion, Phase 2 of NASA's Break the Ice Lunar Challenge involves both an excavation component and a transportation component. That's why the previous webinar focused on emulating the icy regolith for the excavation component, and that's why this webinar focused on emulating the lunar surface for the transportation component. Level 2 of Phase 2 of this challenge involves long-term testing of both the excavation components and the transportation components at a test site of each team's choosing. The requirements for the icy regolith simulant are found in the rules document and were also reviewed in the previous webinar. But the requirements for the simulated lunar surface, which teams will use to transport the icy regolith, are basically open to interpretation. It's up to each team to decide how far they want to take that aspect of their level 2 durability demonstration test. Just make sure you explain and justify your decisions for the judges. And please make sure you use the applicable personal protective equipment like masks or respirators or hoods when working with fine particles that can easily become airborne. It was mentioned in the rules, but I want to be very clear that in the final level, which is level 3 of Phase 2, we will gravity offload the excavation portion of that event. We will not, however, gravity offload the transportation portion of that event. I hope that's clear. We will, however, be requiring teams to transport their excavated icy regolith over complex terrain in level 3. And according to the rules, complex terrain includes rocks, craters, slopes, and loose granular soil. So be prepared for that down the road in level 3 of Phase 2, even if you decide not to include some aspects in your level 2 durability demonstration test. And so that is my presentation on lunar surface emulation for NASA's Break the Ice Lunar Challenge Phase 2 competitors. So I will toss it back to you, Ollie, for, I guess, Q&A instructions.
Great. Before we get into Q&A, I just want to quickly run through the Phase 2 registration form. Where we got a bunch of questions from some folks who are just wanting to kind of go through that process. So I'm first going to share my screen and showcase and just kind of reinforce where it is you will be registering if you have not already, and what that process looks like. So again, just to speak as clearly as possible, next week, September 30th, is the due date for team registration for Phase 2. It is not the deadline for your level 1 submission. It is the deadline to register your team. And what that process looks like is downloading the relevant forms, in these media release and media consent forms, and the eligibility requirements document that's found on the website in rules and eligibility. You'll come here and then you will read the Phase 2 competition rules carefully, and then you will download your eligibility requirements document, complete that, and then upload that via the Phase 2 registration form. So again, you will be submitting your organization, your team name, the affiliation, the country, and then in the United States, if you are to select United States, that would also pop up the zip code of your organization. Then you would input your website, Twitter handle, and Facebook handle. None of this is required. If you do not have, a Twitter or a Facebook, that's completely fine. You can leave this section blank. It's just in the future, we would be able to help socialize and amplify your team via these media properties. Answering if you participated in Phase 1, acknowledgement of the documents I was just mentioning, and then uploading the signed eligibility requirements document, saving it, and then submitting it. So this is what is needed for next week. You are not required to submit your official level 1 submission. That is due the 4th of November. So after you're registering, it's think of it like a checkpoint where we understand how many teams intend to submit a level 1 submission. So hopefully that was clear. I cannot stress enough, just please carefully read the rules and requirements document. It does describe this process and the eligibility process. plenty of teams have been submitting already. So thank you if you've already submitted, and then we can give you a heads up that you're officially cleared to submit for level 1. I do want to just go into level 1 really quickly. And again, this is due the 4th of November. So you will submit your submission title, your technical abstract, any IP property treatments that we should know about, and then you will upload information about your team, and then the related documents, which are the core submittal elements. Again, legal and other required documentation, detailed design report, CAD models, and your durability demonstration test plan. So the thing I want to stress is that in level 1, we are doing a compliance check. So the most important thing you need to do with the submission is carefully read the submission requirements and ensure that your submission elements hit all of the different required elements for durability demonstration testing, for the CAD model design. All of this is on the website. You can go and read about all of this in the judging page. So carefully go through this, because this is just a pretty simple go, no go decision. It's a compliance review. Think of it like that. So, if you are able to carefully read and understand how it will be reviewed in level 1, then you will submit a compliant submission. That said, we also are giving teams the opportunity to submit early. We review, and then we can tell you if you are missing certain elements. So, we don't want you to submit everything at the very last moment, and then it so happens that you miss 2 or 3 elements. After you register next week, we would encourage you to start submitting your level 1 submissions. That will trigger our team to review your submission. And from there, we can identify any issues of non-compliance, and then we'll tell you. We'll say, hey, you're missing X, Y, and Z elements, and then you can update your submission to make sure that it's compliant. So really, we're trying to make this as transparent and straightforward as possible, but it is very advantageous for you if you are able to act early, because we are able to then deliver you a go, no go decision, and that go, no go decision will only occur after you're able to get some feedback. That is, if you're able to submit early enough. So I just also want to go over 1 or 2 questions I'm seeing. A few questions, one of which is in case of late submission on the 30th, can it still be approved, or does all the submissions need to get approved before that deadline? So that question, again, I want to say that next week, the 30th, is a team registration. And if you miss the team registration, you are done. We are not extending the submission deadline, the team registration deadline. We cannot change deadlines. There's no late submission. So please make sure that you get that in by next week. So that's, I hope I'm being as clear as possible. And we are, actively answering questions from team members to try and, make sure that everyone can submit a fully compliant, really plan to move into level 2. We also got a question that was asking if you would be eligible for level 2 if you did not participate and qualify in level 1. No, only those who are compliant and have proven that they have a durability demonstration test plan that hits the requirements will qualify for level 2. So unlike, where you didn't need to be in phase 1, you didn't need to win phase 1 of this challenge to compete in phase 2, you do need to essentially receive a compliance go in level 1 to move on to level 2. And then we have one question here for you, Kurt. Does any level of vegetation in the transportation area to delivery site count against the fidelity score? So if you could just kind of comment on, thinking in the thought process on fidelity.
Before we get too deeply into the Q&A, do we need to bring Pete into operation as a host so that you can help with
I
the
can do that as
Q&A.
well, yeah.
Pete Corrado.
Give me one second.
If you plan to have justification, I mean, if you plan to have vegetation, having trouble talking. If you know you're going to have vegetation, and you say so in your deliverables, you know, we're going to have vegetation, and here's how we justify that it is okay and it makes sense. And then the judges are going to judge that justification. If you know, don't have vegetation listed in your deliverables, and that's what gives you the go to go ahead. And then the judges later on judge your test. They might judge you harshly if you have vegetation that you didn't justify earlier in your deliverables. It's all about, as I said before, it's all about whatever you're testing on, justify it. If you don't want to do slopes, don't do slopes, but justify it. Don't do slopes and not say anything about it. As long as it's justified and you can talk and you can explain to the judge why you chose to do something some way or chose not to do something some way. That's the how we're going to judge the 15% of your level 2 score. So, you know, keep that in context. Everything we're talking about is 15% of your total level 2 score.
Great, thanks.
And you can see what all the other percentages are by going back and looking at the rules.
So Kurt, if I could add to that, if you're planning to test outdoors, obviously there's going to be vegetation around unless you're in pretty extreme environment. But the portion of the demonstration facility that you drive your equipment over probably doesn't make sense to be driving it over grass.
Not unless they justify it. That's my point. We're talking about the ground contact surface. I don't care if there's trees in the distance, you know, I'm talking about what the rover drives on. That's your simulated surface that you have to justify to the judges.
Yep. Okay. So
now Ollie kind of implied, and he kind of danced around this earlier, but I'm gonna be straight black and white with you. If you wait till November 3rd or November 4th, and that's the first time you turn in your deliverables, that is very, very, very risky. If you do that and you don't meet one of our criteria, you're out. So don't wait till the last second. We've got teams turning in their deliverables right now, and they're passing that no go criteria already. And you know, they're cutting metal already, so they've got a little bit of a head start. So we're giving you plenty of time. Do not put it off, and only give yourself, you know, one last chance to turn in your deliverables. We're giving you lots of time and lots of cycles in case something is, you know, in case you're confused about something in the rules. We're giving you lots of chances for lots of cycles through if that needs to happen.
Yeah, that's right. And so so there's kind of one or two related questions. One is it possible to increase the video time? We would like to submit a mission animation video. So no, the requirements for the submission are set, and there's no kind of wiggle room. And you do not need to be submitting a mission animation video at this stage of the challenge.
I would encourage you to post things like that on your own social media channels, and maybe they'll go viral, and you know, that'll make everybody happy, but it won't be judged.
Yep. And then we've kind of talked about this, but I just want to again reinforce. So when we receive questions about our level 1 proposal, are we expected to rewrite the proposal or just answer the questions? So, and correct me if I'm wrong, Kurt, Pete, but really it's more like you just upload and you send to our admin email a version 2. So let's say, you know, you miss 2 or 3 elements. You're not rewriting the proposal. You're just either adding or refining maybe a paragraph here and a paragraph there to make sure that your approach is fully compliant. And then there is another question: will there be level 1 winners, or in this case, that all teams that pass level 2 are the same and there's no distinguished winners? That's exactly right. In level 1, there will be no winners. Everyone essentially receives the same go pass and will receive an equal share of the prize money that's allocated to level 1.
Yeah, and the great thing, so some teams might be a little stressed that we're kind of maybe rushing them to turn in their level 1 deliverables maybe before they feel like they want to spend a little more time and wait till the last second. But the thing about the level 1 deliverable is it's just to check and make sure you've read the rules and you understand everything that you have to do in level 2, that you have to turn into us in level 2, all the data you have to collect in level 2. So if you can put that all in a document and also tell us about the robot you designed or the robots that you've designed, there is an opportunity at the very end of level 2 where you turn in your final deliverable where you can basically correct anything that was wrong with your level 1 deliverable. So we thought we were going to do it this way and we didn't. So this is a change from what we told you in our level 1 deliverable. So the process allows your level 1 deliverable to really not be set in stone, but it is important for us to make sure that teams are understand the competition to a level that they can kind of parrot it back to us in a deliverable, and before we let them move on, because there's a lot of resources involved, and we don't want to waste anybody's time. We don't want to waste all of our judges' time. We don't want to waste all the team's time, and so the level 1 deliverable is a gate. Open Close is going to let hopefully all of the teams that register, hopefully they'll go through that gate. But if some teams, they registered and it turns out they just aren't going to be able to do it, maybe that gate will close on them, sadly. But it's not judged. They're not judged. They're not scored. The level 1 deliverables are just pass fail.
Yep. Okay, so I think we have time for one more question. What feedback comes to acknowledge the team has been successfully registered? So there's no feedback, but I will work with my team to ensure that if you register, we will basically confirm that your registration is compliant and that you have officially registered. So you would just be receiving an kind of confirmation email from the challenge admin, but no other real feedback would come after that. And with that, I think we are going to conclude this webinar. This webinar will be available, as will the slides, on the challenge website under the resources and media section. Within about 2 or 3 days, you have to give us a little bit of time to process the video and upload to YouTube. But with that, we are very excited to get your team registration next week. And then, as we say, we strongly encourage you to start submitting your level 1 submissions when they're ready to go. And we'll just, keep working together. And yeah, thank you very much for participating in this important challenge. And Kurt, thank you very much for today's presentation.
You're welcome. Thanks everybody for your interest. Thanks for attending live, and thanks to everybody for watching on YouTube later. And we look forward to your registrations next week, and we look forward to your submittals. We're excited to look through them and see these innovative and out-of-the-box ideas that you've all come up with for excavating and transporting icy regolith. Thanks.